All right, welcome to the deep dive. You know, I always love when we get to dig into some really complex, really hands-on, practical stuff. And today we're going to get a real pilot's eye view, so to speak, of helicopter flight controls.
Mm.
You send over some pretty incredible material on this.
Absolutely. A ton of great stuff to unpack. And you're right, it's very hands-on, very dynamic when you're actually at the controls of a helicopter.
Yeah, so our mission for this deep dive is, I think, pretty straightforward, but also super crucial to really understand fundamentally the ways a pilot actually commands a helicopter, makes it do all those incredible things that they do.
Right, because when you see a helicopter, performing these seemingly impossible maneuvers, it all comes down to, in the end, the pilot's precise manipulation of just a few key controls.
Right.
So, yeah, we'll zero in on those, the big three, as they're often called,
Yeah.
collective pitch, cyclic pitch, and then those anti-torque pedals.
Right.
And we'll also make sure to touch on the vital role of the throttle, kind of in the mix with all those.
Okay, so let's jump straight into it. Starting with the collective pitch control, it's pretty clear from the source material that this is kind of the primary way a pilot can actually get a helicopter off the ground, gain altitude. It's that lever over on the left side of the cockpit, operated with the left hand. So what's the core function of the collective? Let's unpack this a bit.
Yeah, so think of the collective pitch as the master lever for overall lift in the helicopter. When the pilot, raises or lowers that collective lever, it's simultaneously changing the pitch angle or the angle of incidence of every single main rotor blade.
Okay.
And it's changing them all at the same time by the same amount. So it's like adjusting the bite each blade is taking out of the air all at once, if that makes sense.
So pulling the collective up makes all the blades angle upwards more, which gives you more lift, more bite for takeoff. And pushing it down kind of reduces that lift, brings you back down.
Precisely. You got it. So mechanically, this happens through a pretty clever system of linkages. The movement of that collective lever in the cockpit directly translates into a change in the pitch angle of the blades right there at the rotor hub. And our source even mentions, which I think is pretty cool, an adjustable friction control that's actually on that collective lever. So that's like a safety feature, basically, to prevent any kind of unintended or accidental changes in the pitch.
Okay, the mechanics of it, that linkage system, that makes sense to me. But what's the actual direct effect on the helicopter's flight? So more upward angle on those blades equals more lift, more bite, but I feel like there's got to be a catch, something else going on there.
Yeah, you're exactly right. There is a catch. So increasing that pitch angle on the blades, it does give you more lift, but it also increases the drag on each blade. More drag means that the rotor's rotation speed, that all-important RPM, is going to want to decrease. And on the flip side, if you reduce the pitch, you get less drag, and the RPM tends to increase.
And our sources really hammer home the fact that maintaining a constant rotor RPM is just absolutely critical, non-negotiable for safe helicopter operation. Why is that? Why is that such a huge deal?
Yeah, it's a really huge deal. So a stable rotor RPM is vital for maintaining consistent lift, obviously,
Yeah.
but also the pilot's control authority, their ability to actually control the helicopter. Because if that RPM drops too low, the blades can stall, which is a sudden, very dangerous loss of lift.
Oh, wow.
And then if it spins too fast, well, you could exceed the structural limits of the entire rotor system, which is obviously not good.
At all.
Yeah, so the pilot needs a way to constantly manage and regulate that RPM very precisely, and that is where our friend the throttle control comes into play.
Ah, the throttle. And as our sources point out, that's often located right there on the collective itself as a twist grip. So how does twisting that grip help manage this very, very sensitive balance of rotor RPM, especially when you're also using the collective pitch lever at the same time?
Right, so the throttle's main job, its primary function, is to control the engine's power output.
Right.
And obviously that directly affects the engine's RPM and therefore the rotor's RPM. In most helicopters, and our source actually specifically notes that this is the most common configuration with a counterclockwise rotating main rotor, twisting that throttle grip counterclockwise will increase the engine RPM, basically giving you more power. That way you can maintain the rotor speed even when you're increasing the collective pitch at the same time. And then twisting it clockwise will reduce the engine RPM.
Okay, so just to make sure I'm following, if I'm lifting the collective lever, which increases the blade pitch and the drag, I'd also need to be simultaneously twisting the throttle to give the engine more gas, so to speak, to keep the rotor spinning at that perfect, correct speed. That sounds like it demands some pretty serious coordination from the pilot.
Yeah, it can. It certainly can, especially in older helicopters or simpler designs where they don't have the same level of automation.
Hmm.
And that's where these systems that we call governors and correlators come into play. So a governor is essentially a sensing system. It continuously monitors both the engine RPM and the rotor RPM, and then automatically makes adjustments to the engine power to keep that rotor RPM exactly at that pre-selected constant speed.
Oh, nice.
Yeah, it's really helpful,
Yeah.
obviously. And those are quite commonly found in turbine-powered helicopters.
Okay, so the governor is kind of taking care of that automatically based on sensors and adjusting things very rapidly.
Right, exactly, yeah.
What about a correlator? How does that differ?
So a correlator is kind of a more mechanical solution to that problem.
Hmm.
It's basically a direct linkage between the collective lever and the throttle mechanism. So as you raise the collective, the correlator is mechanically increasing the throttle setting.
Oh, okay.
And of course, as you lower the collective, it decreases the throttle. Now, it's not as precise or as responsive as a governor system, and it often requires some fine-tuning by the pilot, still using that twist grip throttle. But it does provide a significant degree of, I guess, automated assistance.
Right, okay.
It helps keep that RPM within an acceptable range.
So you have kind of varying levels of automation and assist there. But what about helicopters that don't have any of these features? Our source really stresses the pilot's, direct responsibility for that coordination in those cases.
Yeah, for sure. In helicopters without any kind of governor or correlator system, the pilot's skill and experience are really paramount.
Right.
So when they raise the collective, they need to very smoothly and at the same time be increasing the throttle just the right amount to counteract that increased drag.
Yeah.
Otherwise, that rotor RPM is going to drop.
Yeah.
And, the opposite applies when they lower the collectives. They have to decrease the throttle. So it's really a continuous hands-on balancing act, constantly paying attention to the rotor RPM indicator.
And our source even gets into the weeds a bit for piston engine helicopters, mentioning this kind of interplay between collective pitch and manifold pressure, and then the throttle and RPM. It says that generally the collective is the primary control for influencing the manifold pressure, and the throttle is mostly what governs the RPM, but they have these secondary effects on each other.
Absolutely.
It sounds like it's all, very tied together, and the pilot needs to be aware of a lot of different indicators at the same time.
Yeah, and Figure 3.3 that you sent me, I think, illustrates this pretty nicely. But basically, if you change the collective, that has a kind of knock-on effect on the engine's resistance, how hard it's working. And that's reflected in the manifold pressure. And then similarly, if you adjust the throttle to change the RPM, that's going to also have an effect on the load on the engine, which in turn affects the manifold pressure. So the pilot really has to be monitoring both that tachometer for RPM and that manifold pressure gauge to make sure they're making the right adjustments.
Wow.
So yeah, really intertwined systems there.
Wow, yeah. Okay, collective and throttle, a very intricate kind of dance of lift and drag and power management. So let's move on now to the cyclic pitch control. This is that stick that's on the floor, typically situated right between the pilot's legs. And I gather that this is how you essentially tell the helicopter where to go horizontally, forwards, backwards, side to side.
Exactly right. So the cyclic pitch control, that's what gives the pilot control over the helicopter's direction of travel, forward, backward, left, or right. And at its core, what it's doing is tilting the entire main rotor's tip path plane in the direction that the pilot wants to go.
So if I'm pushing that cyclic stick forward, the whole spinning disc of the rotor blades is tilting forward, and that's what's pulling the helicopter in that direction.
Precisely.
Okay.
And as our source explains, the total lift force that's generated by that whole rotating rotor system, that's always perpendicular to that tip path plane. So just by tilting the disc, the pilot is effectively redirecting a component of that lift force, so it's got a horizontal component, which pulls the helicopter in that direction.
Okay, that makes intuitive sense to me. Push the stick forward, go forward. But then our source mentions this kind of non-intuitive mechanical thing, something about the pitch angle of the blades changing approximately 90 degrees before and after the direction of the cyclic displacement. So what's actually going on there? Why that weird offset?
Yeah, it's a really crucial concept that's tied into what's called gyroscopic precession,
Okay.
because that rapidly rotating rotor system behaves just like a gyroscope. If you apply a force at one point in its rotation, The resulting effect is actually felt 90 degrees later in the direction of rotation. So if you want to tilt the rotor disc forward, the mechanical linkages that connect the cyclic to the blades, they're designed to decrease the pitch angle of each blade as it's passing the right side of the helicopter and then increase it as it passes the left side.
Wait, hold on. So if I want to go forward, the blade that's about to be at the very front of the helicopter, that actually has its pitch decreased. And then the blade that was just at the back has its pitch increased. That seems like totally backwards to me.
It does. It seems counterintuitive at first.
Yeah.
But if you think about the immediate effect on lift at those points, it starts to make more sense. So decreasing the pitch on that right side as that blade's coming forward, that results in less lift on that side of the rotor disc.
Okay.
And then increasing the pitch on the left side as that blade goes toward the back generates more lift there. So you have this difference in lift across the whole rotor disc. And that difference is what causes the front of the disc to essentially flap down
Right.
and the back to flap up, which tilts the entire rotor disc forward.
I see. Okay. Okay.
And the source even ties this back to that angle of attack we were talking about earlier, explaining how it changes on opposing sides of the rotor disc to make that tilt happen.
Right, right. It's like leverage almost. It's creating that imbalance of lift to make the whole thing tip. Okay, that's the cyclic. That's our horizontal movement. So now onto those anti-torque pedals. These are down at the pilot's feet, kind of like rudder pedals you'd see in a fixed-wing aircraft. What are they doing? What's their primary responsibility?
So the anti-torque pedals primarily control the pitch and therefore the thrust of the tail rotor. Or in helicopters that don't have a traditional tail rotor, they're controlling some other kind of anti-torque system.
Right, right.
But the main job, the crucial job, is to counteract that torque effect that's produced by the main rotor.
Right, torque. Good old Newton's third law. Every action has an equal and opposite reaction. So as that main rotor is spinning in one direction, the fuselage of the helicopter wants to spin in the opposite direction. And the tail rotor is what keeps that from happening, that uncontrolled spinning.
Exactly. The anti-torque pedals allow the pilot to adjust the pitch angle of the tail rotor blades very precisely. Increasing the pitch creates more thrust, which counteracts more main rotor torque, and decreasing the pitch reduces thrust, or even produces thrust in the opposite direction if you need negative pitch. And that fine control over the tail rotor thrust is what prevents the helicopter from spinning uncontrollably around its vertical axis.
And those pedals are also how the pilot controls the heading of the helicopter, especially when they're hovering, right? The source talks about these things called pedal turns.
Absolutely, yeah. So in a hover, where the helicopter is not moving forward at all, the tail fin isn't doing anything aerodynamically. So those anti-torque pedals become the primary means of controlling the helicopter's yaw, which is that rotation around its vertical axis.
Okay.
So if you press the right pedal, you're increasing tail rotor thrust in one direction, which pushes the tail to the left, and that makes the nose of the helicopter yaw to the right.
Okay.
Pressing the left pedal obviously does the opposite.
But for turning, while you're just hovering, it's all about, very delicately tweaking that tail rotor thrust with the pedals. What about when the helicopter is moving forward in flight? The source talks about maintaining longitudinal trim above something called translational lift. What is that exactly? And how do those pedals, how does their function change when you're moving forward?
Okay, so once a helicopter gains enough forward speed, the airflow over the entire rotor system starts to become much more efficient. And that produces what we call translational lift, which is basically a significant increase in overall lift. And it also enhances the helicopter's directional stability.
Okay.
So at those higher forward speeds, now that tail fin starts to become really effective. It provides a passive stabilizing force. So in that regime, the pedals are mostly used to kind of fine-tune, to counteract any remaining torque effects, and to make small adjustments to keep the helicopter flying straight and level or coordinated.
Right.
The cyclic then becomes the primary control for making those bigger turns, those more significant changes in direction. So yeah, the role of the pedals shifts a bit as you gain more airspeed.
So it adapts based on the flight regime. This source also mentions that the maximum positive pitch you can achieve on the tail rotor is generally greater than the maximum negative pitch. Why would that be? Why design it that way?
Yeah, that's because if you think about it, the primary and most frequent job of that tail rotor is to counteract the torque from the main rotor, which is spinning pretty fast, producing a lot of force.
Right.
So you need a significant amount of thrust in one direction, what we call positive pitch, to counteract that. The ability to produce thrust in the opposite direction, negative pitch, is definitely necessary, for example, during an auto rotation. because during an auto rotation, you have the drag from the engine and transmission, which can actually cause the nose to want to yaw in the same direction as the main rotor's rotation.
Mm.
But that primary need is for strong positive thrust to constantly oppose that main rotor torque.
Okay, so it's kind of like you need more muscle, more power in one direction to counter that main force most of the time.
Right, yeah.
And the source even has this cool figure, figure 3-6, that illustrates how that pedal position directly correlates to the tail rotor pitch and the resulting thrust. And it shows that a neutral pedal position where the pilot isn't pressing on either pedal actually results in a medium positive pitch. It seems like that's key for stable cruise flight.
Yeah, exactly. In cruise flight, the tail rotor needs to produce a specific amount of thrust to constantly balance out the main rotor's torque at that airspeed and power setting. So the neutral pedal position is deliberately set to achieve that kind of baseline level of thrust, allowing the helicopter to maintain a relatively constant heading without the pilot having to constantly make adjustments with their feet,
Hmm.
which could get really tiring.
Right, right. And then
Yeah.
the source also touches on, those vertical fins or stabilizers that you see on a lot of helicopters, saying they play a role in heading control too. Sometimes even with, zero tail rotor thrust in some flight conditions.
Right. So that vertical fin is, aerodynamically designed to provide some degree of passive directional stability,
Yeah.
particularly at those higher forward speeds. So that helps reduce the workload on the tail rotor and, of course, the pilot because they don't need as much tail rotor thrust to maintain a nice steady heading.
Right.
But there's kind of a trade-off there with the size and design of the fin. You don't want one that's too big
Yeah.
because then it could create all sorts of weird, undesirable effects, especially at low speeds or in a hover.
Okay, so it's always about that balance, that compromise. And then what about those helicopters that don't have a traditional tail rotor sticking out the back?
Yeah.
Like those with tandem rotors or those intermeshing or coaxial rotor systems. How do they control the yaw in those kinds of configurations?
Yeah. So in those designs,
Hmm.
even though they don't have a conventional tail rotor, that fundamental need to control yaw is still there. It's all about creating a net turning force around that vertical axis. So with the tandem rotors, which, they rotate in opposite directions, that cancels out the main torque. And what the pedals are doing is controlling the differential thrust between those front and rear rotors. So if you increase the thrust on one and decrease it on the other, that creates a yawing moment. And then similarly, in those intermeshing and coaxial rotor systems where the rotors are also counter-rotating to cancel out that primary torque, the pedals are generally acting to basically create an imbalance in the torque between the upper and lower rotors, in the case of coaxial, or the two intermeshing rotors. And that results in a net torque that actually yaws the helicopter. So it's really clever how they managed to achieve the same thing without actually having that traditional tail rotor sticking out there.
Right. Okay, so even without that familiar tail rotor, the pilot is still using those foot pedals to precisely control which direction the nose is pointing.
Precisely. That underlying, that necessity of counteracting torque and being able to control yaw, it's always there. Even if the specific, the mechanisms that they've engineered to achieve that can vary depending on the helicopter's design.
So we've really covered a lot of ground here, talking about the collective pitch, the cyclic pitch, the anti-torque pedals, and then, of course, that vital role of the throttle in managing that rotor RPM. And I think it's really clear how none of these controls exist in isolation.
Right.
They're all deeply interconnected. And it just seems like piloting a helicopter requires this constant coordinated adjustment of all these things at the same time.
Absolutely, yeah. Mastering helicopter flight is really this continuous process of learning how those controls work together, how they interact with each other, and how the helicopter responds to those inputs in different flight conditions. And really developing that fine motor skill, the muscle memory almost, and then the intuitive understanding to be able to make those really smooth, really precise inputs on all three of those controls simultaneously. That's really what sets apart those really experienced, really skilled pilots. And it's, I think, almost always the case that those small, deliberate adjustments are way more effective than those big, jerky movements.
Well, this has really been a really enlightening deep dive into the real intricacies, the nuts and bolts of helicopter flight controls. It's pretty remarkable, to think that all these fundamental principles that we've discussed, those are what enable all those incredible maneuvers and that unique versatility that helicopters are known for. It certainly gives you a much deeper appreciation for all the subtle adjustments, the constant adjustments that a pilot is making, even when even when the helicopter just seems to be flying along nice and smoothly.
Absolutely, yeah. And hopefully, for everyone listening out there, This exploration has maybe given you a more profound, I guess, understanding of the complexity, the real skill that's involved in being able to pilot one of these machines.
Hmm.
Because it's a whole lot going on beneath those spinning rotors, all that intricate mechanics, all those aerodynamic forces at play, and the pilot is the one who's orchestrating all of that, just with their hands and their feet on those controls.
It's incredible. Well, thanks for joining us on this deep dive. Hopefully now the next time you see a helicopter flying around, you'll have a whole new appreciation for what's going on in that cockpit. Until next time, thanks for listening.